Welcome to the Cosmic Pie Podcast, episode 25, season number 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Right?
We're always updating our equipment and installing updates and bug fixes.
And sometimes we're not, and they still happen.
Yeah, so we had some issues with the cameras today, but we managed to jury-rig something that would work, at least for today's podcast. So,
maybe someday we'll get back to regularly having everything working.
Now, if you have any comments or questions that you'd like to ask throughout the podcast, please use our chat feature, and we will stop what we're doing and try to answer to the best of our ability. And of course, Robert, if we don't know the answers, we'll just make them up, right?
We'll make them up. We'll come up with something.
But we'll keep everything legal.
Oh yeah, legal, yeah.
And that means it's time for the
disclaimer.
Disclaimer.
You wanna do it this time?
I can do it this time.
Okay.
So anything that Rob and I say are just our own personal opinion, not necessarily the opinion of the Department of Physics and Astrophysics, nor the College of Arts and Sciences, nor the University of North Dakota, nor the state of North Dakota, nor the United States of America, nor anybody else that lives in North America, or the planet Earth, or any other planets in the solar system and beyond. Right. It's just Robert and I, and this big, huge, vast cosmos. Just our own little tiny opinion, which really doesn't matter for anything.
Nope.
That make you feel big now?
No. I stopped feeling big a long time ago when I realized we're essentially stardust. So,
Yeah, well, if life only exists here on planet Earth, then we feel much more significant, right?
I don't know. I don't know which way I'd go on that one.
Now, we do upload our recordings, our podcasts on Spotify. So if you're ready to listen to Spotify, feel free to do that. That's usually uploaded by tomorrow morning, so they'll be available. I know a few people do watch on Spotify.
Okay.
So not many.
Just listen, right?
Yeah, no, you can see it. It's both.
You can?
Oh, yeah.
Okay.
Yeah,
I thought Spotify was just audio.
No, it's both visual, and so the full recording is actually viewable on Spotify.
Learn something
which
new
is
every
nice.
day.
And the other thing is it's free.
Yeah.
They don't charge you anything, which is nice. Same as YouTube.
They just collect your data.
Yeah, you just got to wait for the recording to be available. It usually takes like 12 hours or something.
Yeah.
That's why we can't upload them immediately after our podcast is over. We have to wait till the next day.
Yep.
Now, we shall begin. And today's beginning is a bit of an update of something that we talked about a lot in the past. In fact, we had a guest speaker who's a chief scientist on the Europa Clipper mission. And I should have noted what was the episode of the podcast that we had her on, but Bonnie...
we got 3 seasons worth of stuff now.
I was getting up there.
Getting a little difficult to go back and find one.
Yeah, so Bonnie Beretti was from the JPL, was chief scientist on the Europa Clipper mission. And so she talked about what the Europa Clipper is all about. So it's a spacecraft that was launched just a few months ago, whose purpose is to go to Jupiter and survey primarily Europa, one of the main Galilean satellites of Jupiter itself, but also to investigate all of the Jovian system. And there are a lot of instruments on board, but most of these instruments are fine-tuned, if you like, in terms of their ability, is to try to penetrate through the ice that covers the surface of Europa.
Right.
The hope was that there is an ocean under the ice.
Right.
So a subterranean ocean, and that ocean may support life in some form.
And here's the thing, folks, is the reason we're looking for the ocean and we're hoping there's an ocean there is there's a lot of lines of evidence that say there needs to be. And if it turns out there's not, well, we've got some weird physics and chemistry going on.
Well, Robert, so here's the idea. In order to show that there may be life, is that you can drill down through the ice if you have the technology. And of course, it depends on how deep it is. And that ice is going to be hard. How hard, Robert?
It's going to be like rock. It's going to be like granite.
Yeah, so we're not talking about the strength of the ice that you pull out of your freezer from looking at the ice cubes type of stuff.
This stuff is significantly below 0 Fahrenheit. So, yeah.
So if you had the capacity to drill down through that ice, and when you drill down through, you get, let's say, to an ocean, and then you grab, some kind of a sampling of the water and bring it back up, and you see sardines floating.
That's pretty convincing evidence that there is life. Yeah.
It's just like someone once said, how do we know like there's life on another planet if we had one probe and we landed it somewhere? So let's say you land a probe in the middle of the Sahara Desert on Earth. Would you think that there was life on Earth? That that's the only information you have is after the probe lands and kind of maybe has a little camera that does a 360-degree survey around, and you see nothing. What would you say about the planet Earth?
It's a dry desert planet.
Don't go here.
Don't go here.
Yeah, I didn't see a golden arches anywhere, so you'll starve to death.
Yep. There was that box with gold letters on the front, our gold box on the front with black lettered, Dollar General or something. There's a meme about that, folks. Sorry.
So the point is, just one random location on a given planet may not tell you a lot. That's why you really need to do survey from high up.
Right. And me, I was aiming my comment at the fact that we don't know for 100% that there is an ocean under that ice. And we don't know how deep it is, if it is there. So that's one of the reasons why we're looking at radar.
Now, so unfortunately, we can't drill down through the ice with Europa Clipper. It doesn't have the technology to do that on board.
Right.
And so this spacecraft is going to remain in orbit around Jupiter with close flybys of the Galilean satellites, Ganymede, Europa, Io, and Callisto, and then in particular focused on Europa.
Right.
And the orbit that it's going to be in is designed for that.
Right.
Okay, hence the name Europa Clipper, not like Galilean Clipper or something. Right?
It would be really hard now that I'm thinking about it to put something in orbit around Europa, because you're falling down into Jupiter's gravity well, which means you're going to be screaming as far as speed. And then you got to put on the brakes at just the right time that you clip into orbit around Europa. Wow.
And that means you're carrying rocket on board, chemical rocket usually. And that would mean that means the spacecraft is going to be a lot more massive on launch from the Earth, which means you're going to need a lot larger rocket, which means a lot more money. And that's what it comes down to, money.
Right.
And we know nowadays with the budgets the way they are, money is a big, big deal.
I think we'd have to probably do something like we did with the Huygens probe on going on Cassini, going around Titan, or dropping onto Titan. Cassini itself was going around Saturn, so our probe would have to go around Jupiter and then drop something off on a flyby of Europa into Europa's orbit.
Well, the other thing to keep it cheap is you could put, let's say, ion thrusters on board.
Right.
And you could use that to just ever so gradually alter your orbit in such a way that eventually, using the gravitational deviations that you would get from the other satellites around Jupiter and even Jupiter itself, to eventually go into orbit around Europa. I'm sure there's sophisticated computer programming.
I'm sure we can figure it out, but
Yeah.
it's not a trivial problem at all.
No, and the other thing too is I remember if you look at space exploration of the solar system, like back in the late 60s, very early 70s, a lot of times we flew directly spacecraft to these planets.
Right.
Where when we get into the late 1970s, the spacecrafts were designed to do a lot of these flybys that you see. So to go to some planet, you would fly by, pass by, let's say, Venus or Mars, and come back to the Earth again, and back out to Venus, and then back to the Earth, back to Mars. So you do all this. Why don't you go directly? Because it costs a lot more in terms of a rocket, in terms of the overall size that you need, and therefore money, dollars. It costs a lot more to keep things on the cheap. And why do you want to do that? Because the projects wouldn't be approved by Congress if they were too expensive.
Right. And we haven't for decades, going on like half a century now, had a rocket engine with a high enough, as my buddy James, who was on the show once said, the high enough specific impulse to go on a direct flight.
The only thing I could think of that was relatively direct, it was the New Horizon spacecraft that went to Pluto.
Right.
And that's because it had to, but it certainly was much smaller than what engineers or scientists had hoped initially. When you're thinking of what type of spacecraft should we send to Pluto, what are the sort of instrumentations do you want?
Well, they had to cut down on the instrument package because they had to put that much extra fuel to kick it.
Exactly. You
up
want to
to
keep the
speed.
mass as low as possible.
Right. They needed that mass for rocket propulsion.
Right. So that really, really limits you on what you can do.
Right.
And so it's either, do you want your project approved? And if you do, then you got to take this indirect route that could cost you years in terms of how to get to the object that you want to get to. Or do you want to go direct but have essentially almost no equipment on board?
Right.
That's the trade-offs you have
That's
to
the
make
trade-offs.
as an engineer in the space community.
Yep.
So this, the news about Europa Clipper, so it was launched successfully by a Falcon Heavy rocket a few months back. It's due to arrive in the Jovian system in the year 2030.
Okay.
And one of the flybys it did back in March of this year was to fly by the planet Mars. So you can see an image of Mars on the right side taken by the camera. And it's in the infrared, so it's checking out the thermal camera. That's why you don't
Okay.
have this nice crisp view that you normally would think of Mars, taken by lots of other spacecraft that have visited in the past. But the one thing that it did was also test its radar. And this is very important because this is ice penetrating radar. In fact, at the highest energy, it can go down to almost 30 kilometers below the ice,
Oh,
believe it or
wow.
not.
Nice.
So this is up to date, really advanced type of stuff. And you can see the radar instrument on this artist's drawing that you see there on the top left side. The poles that you see sticking out below the solar panels on either side, that's part of the radar antenna itself.
Okay, so this is long wavelength then.
Yeah. So what you see on the very bottom is what we call a radargram,
Okay.
and it is a slice on the equatorial region of Mars taken by the radar unit itself. This was a 40-minute observation, and you can see the different craters if you look along that strip that's near the bottom. So it's just a test of the instrument, and as far as I can tell, the reporting that was done recently, which is why this is in the news. You might say, why is it in the news? It happened back in March. Because scientists had a chance, till now, to investigate and look at all of the data that was sent back to Earth, and they have a full, if you like, suite of everything that happened with the radar. So everything is working nominally, as NASA would say.
Yep.
And that 40-minute slice like this produced 60 gigabytes of data.
Yeah.
So it's amazing when you think about it. That's a lot of information in a relatively short period of time.
And it was able to transmit it through that antenna. So,
Right. So
yeah.
so the Europa Clipper's radar, which is extremely important, is a major instrument on board that spacecraft, works, and hopefully it will continue to work
Now-
when we get around Jupiter in 2030.
I know this slide and this topic isn't about this, but that pole at the top, that smacks of a magnetometer. Is that what it is? Are they looking at the magnetic fields
yeah,
around?
for sure,
Okay.
100%.
All right. Yeah, because when you've seen enough of these probes and satellites, you start picking up on what instruments look like. So,
And the other thing to notice is the size of the solar panels.
right, huge.
They're huge, and the reason for that
Is the light capacity drops off as 1 over the distance squared, and Jupiter is what, 5 times further away
Yeah.
from Earth than Earth is.
Yeah,
so
on
that's
average.
25 times less light.
Right. So you need to make these solar panels huge. In fact, if you didn't have solar panels as efficient as we have nowadays, because people are always improving that technology,
Would have had to have been an RTB.
yeah, you have to go nuclear. This thing is nuclear.
Yeah, to provide the 1.81 gigawatts.
Yeah, the radioisotope thermoelectric generators is what typically a spacecraft in the outer solar system would need to use. And so,
And
yeah, it's very
hello,
important.
Extrabulla, by the way. We do see you.
Now, the next slide is an event that's coming up in a few days from now, and this is the annual Perseid meteor shower. Now, the slide I'm showing here was put together by others, and notice they misspelled Perseid.
Yeah.
So unfortunately,
yeah.
I can't change that without the slide looking kind of crappy
Well,
in
that's
that
because
area.
they spelled it like it's usually pronounced when
Right.
it should be Perseid.
Right.
And most people say it like
Perseid,
you did.
at Perseid meteor shower. Now, just to give you an idea what this is all about, so every time around August 11th and August 12th, we have this meteor shower that occurs. It's due to the fact that the Earth, if you like, intercepts the debris left over from comet Swift-Tuttle.
Okay.
So Swift-Tuttle in its orbit around the Earth, I forget its orbital period, it's several years, if I remember right, 5-6 years or something of that order.
Right.
And as comets go along, like in this case, it's a closed orbit. It's not one of these objects that only swing by the sun once and then forever lost. Like we've talked about other objects like 3i Atlas. right?
Which we've got a question about that. but
Okay.
Yeah.
But yeah, so this comet then is a bounded orbit, but as it travels in its orbit around the sun, it deposited dust and particles.
Yeah.
And those dust particles is what the Earth hits or intercepts that part of the orbit every middle of August, essentially. And those are what we see as the shooting stars. So you get this big enhancement over a period, it can be several hours, of a lot more shooting stars than normal, right? So you can somewhere up to values of hundreds of them.
And I hate to tell you folks, but the best time to see it is when we're turning into the stream, which will be in the wee hours of the morning.
Which I'll show the reason for that here in a second. But yeah, so this is coming up. It's worth looking at. Every year I try to get out and see this. But the problem is the moon is going to be in the way this year.
Oh,
it's going to be a little bit past full moon. So it's a waning gibbous.
And most meteors are not that bright, folks.
Yeah, so it's going to ruin the observation. So this is not particularly a good year. And if you live where we live in North Dakota, in fact, if it's clear, there may be a lot of smoke in the air.
Right.
And that'll cut down, even if there was no moon to worry about, that would cut down a lot of the meteors. In fact, and not to go too much into this, the smoke's been so bad at times this summer, you can't see a single star in the sky at night.
Right. It's been bad.
Yeah, it's been pretty awful.
So shall we get to that question? By
Sure.
the way? Okay. So Extra Bulla asks us, what's your opinion of using the current Juno probe and diverting it to intercept 3I Atlas? And the problem is Juno's in orbit around Jupiter, so you would have to have a rocket on it with enough fuel to first get it out of Jupiter's orbit, and then would have to race to catch up to 3AI.
I think if you really wanted to do this,
yeah,
I think the best bet is to build one of these micro-like satellites that you see.
Right.
That you can outfit it with some cameras, maybe, if that's all you want. If you have the mass storage that you could use and put something else there, maybe taste the environment around, like a mass spectrometer, taste the environment around the object.
The three instruments I would really want is a camera, a mass spec, and a magnetometer.
If you can get one or more of those instruments on a real tiny satellite with maybe some thrusters for maneuverability, stick it on the largest rocket we have, like the SLS.
Oh yeah.
And then launch that sucker.
You could get that up to enough speed.
You could probably be able to track it down and do an encounter. And the other thing is, you might blow right by it. At 10 times the speed of a rifle bullet.
Right.
So you only got a limited time to make direct observations, but at least better than nothing. And if you had the ability, the thrusters on board could slow it down like another rocket to actually be able to have more time to make the observations. But let's say that the bare minimum you'd want a camera to be able to see, multi-filtered, of course.
Multi-filter.
And have it as small as possible with no thrusters on board except some steering thrusters to make sure you intercept the target. And then stick it on the SLS and away it goes.
Right. And so we're follow-up question, it's supposed to get within 53 million miles of Jupiter. Could the probe take readings from that far? And the answer is it could take a picture, but it would be a dot.
Yeah, and the camera is...
So...
And the other thing is, if you think about, let's say, pictures, Juno was initially proposed not to have a camera.
Well, where's the fun and point in that?
And that was what was said.
Okay.
So the people who are at, they approve all of these projects for NASA, they go through all these endless panels of, of review and stuff. Somebody said early on that, wait a minute, the public wants to see pretty pictures.
Right.
So maybe even though it's not impactful to the science they want to get out of this instrument, let's put a camera on board.
Well, I mean, a good CCD is, a few ounces, and a filter wheel kicks it up to maybe a pound. If your payload can't handle that, I'm curious as to what the hell you're doing. Sorry.
Well, the funniest thing I find is anytime there's a press release from Juno, they always stick an image.
Yeah.
So they definitely use that. But I think taking an observation, even if you point the instruments towards the comet, it would be pretty poor resolution. And I think you'd be better off taking the James Webb Space Telescope and the Hubble Space Telescope and training. The problem there, of course, is that they're close to the Earth compared to Juno, and the Earth's on the other side of the sun, when the comet reaches the closest approach to the sun itself, unfortunately.
But yeah, I get everybody's interest in these things, but the Europeans have a mission proposal on tap. It's getting the funding and proving that it's scientifically worthwhile. Have the best idea for getting to an interstellar interloper like Atlas, 3i Atlas. And that is to just go ahead and have some satellites out at Lagrange points ready to go with
Right.
huge thrusters. And when seeing coming in, you scream those bad boys out at it.
That's the better way to do it.
Absolutely. That's
So-
pretty much the only way to do it. These
Yeah.
things are moving way too fast to do it otherwise.
Unless you have like billions of dollars and you could have a team to work on this stuff and do it immediately.
Yeah.
You know, that's the kind of thing you're up to, is the timeline is relatively short.
It's
I
short.
mean, October is closest approach to the sun.
Right.
So it was discovered several months ago, right? A couple of months
Mm-hmm.
ago back in early July, whenever it was. And it was announced first part of July. So how much time do you have to design something and launch it and get it out there?
You've got months to design. You've got months and it's gone.
You know what it reminds me
yeah.
of now? The Martian movie.
Yes.
Remember when the resupply vehicle failed on launch?
Right.
And then now you have so many days to design. Remember?
So many days to design a new approach.
Yeah, it's almost like that kind of a pressure environment.
So anyway,
It would-
it's a good
it-
question, but yeah, no, unfortunately Juno's trapped in Jupiter's gravity well. So.
Yeah, it doesn't work out. Now, the Perseid meteor shower, you think of where does the name comes from? It comes from the constellation Perseus,
Perseus.
right?
Yeah.
And the reason why the meteor shower is named after that, because we always named it after the point on the sky where the meteors seem to be coming from. It's called the radiant point, and that's because the Earth is going in that direction. And so it's almost like watching, I guess, rain coming towards you when you're in a car or in a snowstorm, and you see the snowflakes are always coming from the front. You never see them coming from the back,
Right.
right? Or
Even
the
though they are
side.
back there.
Yeah, or the
Are
side.
there. Yeah.
Because it's our motion through those stream of particles. In this case, of course, we're talking about the dust, really fine, small dust particles that were left behind by that comet. And so that's our sort of overall motion. Now, this radiant point is very low in the sky
I'm
at
noticing that.
at the beginning
Yeah.
of the night and rises more and more throughout the night. So it turns out the higher up the radiant point is, the more of the shooting stars you can see.
Less atmosphere. Yeah.
Well, no, because if it's
Oh.
around the horizon, you're only going to see the ones that happen to be going above the horizon in that direction. You're going to miss all the 100 and the other 80-degree view that's below the horizon.
Yeah.
So if the radiant point is way above your horizon, your local horizon, then you're going to see all of the ones that are produced coming
it.
from that radiant point. So it's always been traditionally the best viewing time is the few hours before sunrise, before the daylight comes near the end of this.
And I will point out that it's usually fairly easy to find Perseus. It's a dim constellation, but if you see that star Capella, that is, if I'm remembering correctly, the fourth brightest star seen from the northern hemisphere.
Or look for the W.
So, or look for the W of Cassiopeia and
Right. So if you're in a dark site, of course, especially, and that's the other thing we should let people know, that to really see the meteor shower, you need to be in a dark site, or you should be, to see it
Right.
at its best.
because otherwise you're not going to see these things.
Yeah, you're
I
only
mean,
going to
it's-
see a few bright ones, and that's about it.
Yeah, and bright ones are rare.
And the other thing,
fireballs are even rarer.
yeah, and the other thing to note is if you're not, let's say it's cloudy the day
Yeah.
of the meteor shower, then you can also look, several days afterwards and several days before. They
Right.
ramp up in activity. It's not do or die. You have to be there only that few hours or something.
Right. It's not like turning on your shower and turning it off again in the morning. You
Yeah.
know, nothing like that.
So given where we are now on the 5th of August, the Perseids are out there now. You see the
Yes.
odd one, and then that'll get more. The activity will increase as we get closer to the August 11th, August 12th sort of time frame for that. Now, the other thing I wanted to show or talk about is a comparison. We talked about them already, the James Webb Space Telescope, which is an infrared telescope, mainly, and the Hubble Space Telescope, which is mainly an optical telescope, although there were instruments to look in the ultraviolet and in an infrared, is a comparison of looking at a similar field of view. So the Hubble Space Telescope, so the way this works is there is the director of the Space Science Institute, which runs both the Hubble Space Telescope and the James Webb Space Telescope.
Right.
The director has discretionary time. So if you propose to use, let's say, the Hubble Space Telescope, what you ask for is a number of orbits.
Okay, yeah, because its orbits are 90 minutes. Though,
Yeah,
right?
and then if you're pointing on one side of the Earth, you have roughly about 40 minutes of observation you can make before
Okay.
the telescope then is going on the other side of the Earth, and you got to wait till it swing out around the backside of the Earth relative to the location of your target, and then you can observe for another 40 minutes.
Right.
So on each orbit, depending on where you're looking, of course, you could get, as little as 40 minutes of observer time, roughly, let's say on average.
Right.
Okay. So when you propose, then they'll award you a certain amount of time, which is in orbits. But the director of the institute has a certain block of orbits that they can use to their discretion. So, for example, a new object is observed, the three-eye atlas, right?
Right.
It wasn't there when it was time to propose. So you could get a hold of the director and say, hey, I'd like to use the Hubble Space Telescope to look at this object.
Okay.
Okay, it's something that just appeared. So they can assign the observation from their pot of orbits that they have on their disposal, this discretionary time, and say, okay, I'll give you 2 orbits or 3 orbits or whatever you need to observe the object.
Okay.
Now, one of the things that happened in the past is that the discretionary time had built up to the point where the director said, I should do something with this time. I have a lot more than what I can really use. So let's take the Hubble Space Telescope and let's stare at a blank area of the sky. Now, why would you do that? Because to a telescope, there's nothing there. There's no bright stars in the way or a bright galaxy in the way. But to the Hubble, if you stare at that spot, you're not going to be inundated by all this light coming from nearby stars that would saturate the detector.
Right.
So you're going to look in an area that's relatively dark. But if you expose long enough, that darkness then will expose all of these objects that could be there, like very faint galaxies
Or
and even faint
will it?
stars.
Or will it? At the time, we didn't really know.
So that was the idea. So they looked in this really small area of the sky near the Big Dipper, and that became known as the Hubble Deep Field. And the field of view of the Hubble is extremely small. It's like looking at the size of the eye in Abraham Lincoln on a penny or something, held arm's length.
Okay.
That little tiny field of view. That contained on the order of 3,000 galaxies.
Right.
Well, once that was done, then people said, hey, this is a good idea. So when they put better instruments on board the Hubble through repair missions from the space shuttle, they decided to do the same kind of thing. Let's stare at a certain area of the sky. So it became like the Hubble ultra deep field, just to make it different from the deep field and so on. Then I think there was the extreme deep field after that. So what has happened is the image you see on the left is the one taken by the Hubble Space Telescope of the ultra deep field. So most of the objects you see in that image are galaxies.
Pretty much all of them aren't they?
Well, there's a few objects you see there with the
there's the
diffraction
spikes. So,
spikes.
yeah.
Those are stars. Okay. Now, the same field of view, it's just oriented a little differently. It's tilted a little different. Is taken of the ultra deep field from the James Webb Space Telescope, and that's the image you see on the right.
Right.
Now remember, number one, the James Webb Space Telescope is a much larger telescope. It's 6.5 meters across compared to the Hubble's 2.4 meter aperture size of its mirror. And the other thing is the James Webb observes at infrared wavelengths, not at optical wavelengths, which is the image on the left. So the optical or visible part is on the left, and the infrared is on the right.
And I've been trying to match up these fields and can't do it.
It's very difficult
Yeah.
to do that because of the difference in the wavelength
Wavelengths and the resolution and
and the
everything
size,
else.
yeah. So anyways, so we have, if you like, not only the optical data, but then you can go back and mine then what you see in the infrared.
Right.
And we always know that in astronomy, for example, if you just observe like a Galileo, you just observed in the optical, you would miss a lot of phenomena that exist in our universe, because a lot of the phenomena only produces, let's say, at radio wavelengths,
Right.
or maybe at X-rays or ultraviolet, and you're not, or infrared. You're not going to see any of that if you use just an optical telescope. So if you want, no pun intended, the big picture view of the universe, you do need to observe at all the different wavelength regions of the electromagnetic spectrum. So starting at the longer wavelengths, it would be radio, and then you get into the microwaves, and then you get into the infrared. Then you're into the optical, so you go red, and you make it all your way until you get to blue violet. Then you're even shorter in the ultraviolet. Eventually you end up in the X-rays and then the gamma rays.
So,
And if you had telescopes then that are designed to look at all these different parts of the electromagnetic spectrum, and the design of the telescopes have to be different. You can't take an optical telescope and go try to collect X-ray photons with it or gamma ray photons.
that's not going to work.
It doesn't work. So you need these different telescopes that are sensitive to different parts of the electromagnetic spectrum, and put all that information together to get a more complete, if you like, view of what's out there.
Yep. We do have another excellent question from Tanith Rosenbaum. How do they actually do long-term exposures if you only have 40 minutes of continuous observing time, image stacking, or do they close the lid and reopen it in the next orbit?
Yeah, so that's exactly what you would do.
Is image stacking.
Yeah, you would close up the camera, so you do an exposure, let's say maximum 40 minutes. And then you would take another exposure of the same region. And then after it's over, let's say you collected 10 observations, then in the computer you can just shift them so that they're on top of each other, the identical objects, and stack them together.
Right.
And the other problem, I should mention that over time, since the Hubble especially is above the protection of the Earth's atmosphere in terms of cosmic rays, each image that you take of the sky is going to have a ton of X-ray, cosmic ray streaks on the image.
Right.
And those you wanted to avoid. And so what you do is take shorter exposures, a lot of them, and stack them together, and you can reject. If you see a streak in one image and it's not in any of the other images in the same location, it's a cosmic ray. You can reject that and fill in those pixels with data that's not hit by a cosmic ray strike. So you can reject the cosmic rays, but you need multiple images to do that.
And even on the ground, we get cosmic ray hits, and they're easy to reject because they're bright. They're high energy particles. They slam that CCD. They actually do physical damage to the chip.
Yeah. So, I mean, on the ground, they used to do this in the old days of photography when they took photographic plates. They were like 1% efficient. So with every 100 photons that strike the photographic plate, only one actually gets recorded when you develop the plate. And yet they would take observations of galaxies that were like 36 hours of exposure. And you're thinking, wait a minute, the night is not 36 hours long. What? Because they would observe a galaxy, let's say for 8 hours one given night. They would block the detector, the photographic plate, cover it up with a light-tight container. And then they would point at the same galaxy the next night and open up the camera again and continue that exposure if you point at the exact same spot. So they could build up or accumulate the exposure time over multiple nights. It's a hard task to do, but you can do it.
You can do it.
They proved that you can do that.
Yeah.
You just got to know what you're doing, of course. And with computers nowadays, it's much easier to do it.
With computers, it's a cinch.
Yeah, you can
clicking a few buttons and playing them.
Yeah, so typically you take a few minute exposure, like you could take, I don't know, let's say a 5-minute exposure, and then you could take another one, and then another one, and then another one, and another one, do it for several hours.
Yeah.
And then stack them all together later using software in a computer.
Pretty much how I got one of the best images of the Orion Nebula that I've taken was, like 1 second images, but did them over 40 minutes.
Yes, and you can do that with bright targets.
Yeah.
And amateur astronomers do that a lot. They would take, I remember in the old days, it started with the old webcams. And they would hook it up to telescope, and they could take 1,000 images of very short exposure, let's say of Jupiter, and then it would toss out all of the ones that were blurry, because the seeing changes over the time that you're observing. Just pick the ones that are really the highest resolution, stack those together, and you get this ultra high resolution image of Jupiter at the time.
Right.
So it is a lot of tricks that you can do there.
Yeah. A lot of little tricks.
Yeah, for sure.
Okay. Next slide.
So the next slide then, we're going to talk about the moon. And in particular then, some of the things that have been discussed for many years now, this is not a new topic. And this is, for example, here on the Earth, when you're using a radio telescope, you're affected by interference, radio frequency interference. And that could be due to, depending on what frequencies you're observing at, it could be due to internet, wireless internet, you're picking up by your radio telescope, so earthly things. It could be cell phone communication that you're picking up, any type of transmissions that we're doing. Microwave ovens, military radars, if you're in the right spot. All these different earthly activities that can be picked up by a radio telescope, and therefore that interferes with the signal you're trying to detect, which is usually much, much weaker from some type of extraterrestrial object, like a distant galaxy or something.
I mean, the cosmic microwave background, the first detection of it, they actually didn't believe they detected anything. They went up to clean out pigeon poop out of the horn, the radio telescope's horn, because that produces a radio signal.
Yeah, pigeon droppings happen to emit some photons at radio frequencies that they picked up by the detector.
Right.
And since they're in the horn, they're fed directly to the detector.
To the detector.
So it's a bad place you want to have pigeons living.
Right.
So we always wonder then, how do you get to a clean environment? Well, what they've done in certain places, like in Virginia, is to say, okay, in this little area, cell phones are forbidden. Any type of electronic devices have to be turned off. You can't use them, and so on, to cut down on the interference at radio wavelengths.
Right.
That works to a degree.
Right.
But there's still some issues.
There's
For
still
example,
some leakage.
Yeah, well, there's still satellites in the space.
Right.
In fact, if you ask like Seth Shostak, who wrote a book called The Alien Hunter, and it's about his life of trying to find extraterrestrial, the SETI Institute.
Yep.
And one of the things that I have the books, I read it already.
Oh, okay.
Yeah, so one of the things that and this was a few years back, one of the things that he wrote about is describing what was your best signal that you thought was coming from extraterrestrial intelligence. What happened? What are the steps that you guys followed? And what was the resolution to the fact that it turned out not to be so, right?
Right.
Obviously, or we would know all about it. And it turns out that they got a signal coming from space. It was a strong signal.
Okay.
That right away told them there's probably artificial. It's a very strong signal when you expect this stuff to be extremely weak. When you move the radio dish off the source, it went away. When you brought it back to that same location in the sky, it was there again. And when you went the other way, it went off again. Okay. So they have all these checks. And some of the checks you do, of course, is to say, okay, is there anything in space that would give this signal, like any satellites,
Right.
military or otherwise? So they have a database that they run through checking. And of course, you can also call up your great uncle Bob in Australia and say, okay, when the Earth rotates such that the target is above your horizon, take your radio telescope and look at it. Do you see the same signal? I mean, that was in the movie Contact, where they confirmed it from the observations in Australia. And it turned out they did discover that this signal, eventually they traced it back to the Soho spacecraft.
Oh, wow.
Now, it took a few hours to come to that realization.
Right.
In the meantime, the New York Times had called up and said, I understand you have a signal you're tracking down. It's like, how do you know that? Somebody in your institute or someone else.
Is what it means.
So they always wonder, if you guys ever discover something, you SETI guys, and you have evidence for extraterrestrial intelligence, you'll never tell the public. The government will put a lid on it.
Right? Yeah, right. Somebody will tell.
Yeah, but somebody, they did. So anyways, it turned out to be man-made, if you like, satellite in space that does observations of the sun.
Right. I'm surprised you didn't mention the WOW signal, because
that was a one-time detection,
but it was
right?
a one-time
and you
detection.
you always got to look for confirmation science, right? And that's everything. If you run an experiment and you find a result, I don't know, you detected the dark matter particle. If you never detect it again and no one else can ever detect it, it probably doesn't exist.
That was an instrument glitch.
Yeah, you need confirmation, right? That's how science works.
Yeah.
Check and balances. Now, we always know that then you're looking around, where is a good place that we could put a radio telescope where it's really quiet? We don't have to worry about this background interference. And one of the places that had been suggested is the backside of the moon, the far side of the moon.
Yeah.
We could put a radio telescope there, and the moon acts like a natural shield, preventing any sort of earthly signals from reaching the radio telescope.
Right.
So if you detect anything, it would have to be things that are real, like galaxies or maybe extraterrestrials, and also any other space probes that happen to be out there in that line of sight.
Right.
And those we know where they are and what frequency they're running on.
Because those are very few.
Yeah, like, the Pioneer, well, they're not transmitting that, but Voyagers are still transmitting. The
Right.
New Horizon probes are transmitting. Anything that's out into the outer planets And going to the asteroid belt, we have like Lucy, for example.
Right.
They would transmit. If it happened to be in the same line of sight, then you can detect it if you're monitoring that frequency that they communicate to Earth. But those are much easier to track down than stray signals from earthly things.
From earthly things, right? Yeah.
Now, so here's one of the proposals that have been made, and this came out recently by the Lunar Crater Radio Telescope sort of group, and that is what is the cheapest way we could build a radio telescope on the moon? So here's the idea. Take a crater that's already there. In this case, an example they're using is about 3 to 5 kilometers in diameter you could do this for.
So mile and a half wide.
Yeah, and you could put this sort of deployable wire mesh that's strung out in the bottom of the crater, and you could have then rovers, as you see here at 4 different points, that would hold the detector. So you could pull on the deployable wire mesh to give it the shape like a parabola. So any radio signal would get reflected off the green wire as they're color-coded here, bounce up and hit that detector that's suspended by this reddish type of wires that you see there. And of course, you could do all this stuff if you had rovers, and they could be, autonomous or robotic, so you don't even have to have people here, right? You control all this remotely. And you could artificially then make this sort of radio telescope. Because for a radio telescope, you don't need it to be polished like an optical mirror, because the radio wavelengths are so much longer than the deviation on the surface of glass that are just irrelevant. That's why you can put a radio telescope dish together using pot rivets. It doesn't even know they're there. It seems,
as long as the holes are smaller than a quarter wavelength?
yeah.
I remember my physics
so
right?
you want it as smooth as 1/20th of a wavelength.
1/20th. Okay.
Is a typical optical figure, right, of merit. So if you want to use that same figure of merit for a radio telescope, so you're talking about wavelengths that could be meters in size. So you could easily put the stuff together and have this wire mesh. There'd be a really cheap way of doing it. The only thing that's a problem here, is that now there's more emphasis and more activity, more focus, if you like, on the far side of the moon.
Of course there is.
China, for example, have sent up rovers to explore the far side of the moon. How do you think those Chinese rover can communicate with Earth back in China?
Well, they're using radio waves.
And you know what they do? They put satellites in orbit around the moon, and when the satellite is on the far side of the moon, in the line of sight of the rover, they can send a signal. So, but if you have your radio telescope now on the far side of the moon, it can be affected now by this transmission. So you know what's going to happen. At least here's one possibility. As we go forward in the future, more and more countries are going to have additional things on the far side of the moon, all needing to communicate with the Earth using geostationary satellites that are in orbit around the moon. And of course, those will contaminate, and you'll be back into this environment once again where earthly things are interfering with your radio telescope signal.
Right. And people are like, well, you just need to put it further out, further out, further out. That brings up an extra bullet question. He asked basically, what would it take to put one out like Kuiper Belt or Pluto? And the answer is again, that's a lot of thrust. That's a lot of effort to get something out that far.
And you could do that.
Absolutely.
Right? And you can have it deployable. So hopefully it opens up like an umbrella once it gets out there, because the dishes have got to have a certain shape, unless you're doing very specialized type of radio astronomy where you just need, like, so for example, a dipole antenna.
Right.
Then you don't have to worry about the parabolic shape. These kind of things, you can certainly do that. And that's something that will be done in the future. That's exactly what people are thinking of. Get away from the Earth, get away from our noise, if you like, and therefore we'd be able to be more sensitive to what you'd expect to be very weak signals coming from ET.
Right.
And
because
that's
it
ultimately
would be a weak signal.
Yeah, and that's ultimately what we're looking for, right? I mean, that would be the biggest of all discoveries in all of human history, is discover signals coming from another civilization way beyond our sun.
And we could talk a long time about that, because one of my things is one of the parts of the Drake equation is how long people are transmitting, how long a civilization lasts to transmit radio waves. Well, we're beginning to find out from our own development that you don't have to wipe yourself out to stop transmitting radio waves, because we don't broadcast very loudly into space anymore.
Yeah,
because everything's directed, everything's laser and fiber optic and directional antennas, and so that time window of an alien civilization transmitting openly may only be 100 years, like it's proving to be with us.
that's right. And the only thing that has the strength that can go out a long distance is military radars.
It's military radars.
That's the biggest, right? Is that so that could last for a long time? Who knows? But still, in terms of the age of the galaxy, that's still just a little tiny drop. Exactly.
Yep.
So that's the argument, right? If there's a few intelligent civilization out there, you have to be listening at the right time when they're broadcasting.
Right.
And the other thing is you got to allow that signal to reach us.
Right. So, don't give up hope, but at the same time, these are things you got to take into account when you start speculating on this. Don't get your hopes up, but at the same time, is it worth looking? Absolutely. Absolutely.
Well, when they first looked, there was speculation that civilizations that were broadcasting at radio frequencies were all over the place.
Right.
Almost every star would have a planet with life on it that would do that.
And we've now found every star does have a planet, but
They're not broadcasting.
they're not broadcasting.
We would have picked their signals up by now.
Right.
So that puts constraints on how rare is life. And some people say it's extremely rare. Other ones not so much. It's not really that life is rare. It's that intelligent life.
I think intelligent life is rare. I'm in that camp. I think life is going to prove to be everywhere. Intelligent life is going to be really rare.
And one of the things we look for, of course, is the building blocks of life, like
Right.
amino acids.
Amino acids
And
other
complex organic
complex
molecules. And we talked about that in the last podcast. That you can see all the time, we're seeing more and more regions in space where these things are being discovered. So the basic building blocks would develop RNA and then DNA, this kind of stuff are out there.
Are out there
It's just
and common.
did things come together in the right way? So then life formed. And how did that life evolve? Was it able to get out of the stage of being multicellular at a very low level to something that's organic in some sense, right? Highly complex like us.
Yeah, and that's the question. And so, I'm in the camp. Bacteria, microbial life, everywhere. Complicated, multicellular, much more rare. Intelligent life, we may be one of one or two in our galaxy. But until we got a sample size bigger than one, it's all speculation. It's all spitballing.
Yeah, that's the thing too. And even if you get to the low, like stuff close by, like the moon or even Mars, there's a lot of cross-contamination, as we know nowadays, that come from the solar system itself.
Yep.
So you still have to guarantee that you didn't bring those creatures there, or that somehow they're on a rock that survived, like bacteria. An Earth rock that got ejected into space millions of years ago and then landed on Mars, and that's what you're seeing now.
Right.
And there are ways of doing that. All of the cryality argument, where all organisms on Earth are right-handed in that sense.
Chiral, yeah.
Yeah, and then if you detect life form, let's say that's on Mars, that's left-handed, then I think that's the thing, that then you almost 99.99% guarantee that that's not from the Earth.
And that's one of the things about biology that they're still questioning. Why is all life on Earth right-handed chirality? Why are there no life forms on Earth that have left-handed chirality? Energetically, there's no difference. So,
Is there a place in the universe where life is made up of nothing but antimatter?
show me an antimatter star first, then we'll start talking.
Anti-human.
An anti-human. You come into contact and explode.
You annihilate
and destroy
instantly.
the old sector.
Wow, there's nothing to prevent that.
There really isn't.
And you could have an anti-Earth
Yeah.
made up totally of antimatter.
Yeah.
And they would name things matter, but for us, that's antimatter.
Because they did find that they have created molecule, an atom,
Hydrogen
of
atom.
antimatter, a
Yeah.
hydrogen atom. So these types of atoms do form, but my point is again, show me enough antimatter to form an anti-star, and now we can start talking about anti-Earth.
Well, it could be a parallel universe.
Could be.
Composed nothing but antimatter.
As Extrabula pointed out, he and I have had many discussions on speculating and things like that. So,
Well, talking about the moon,
yep.
there was a recent study done that's related to the Artemis project, going back to the moon, and hopefully setting up permanent scientific basis, sort of like what we have in Antarctica.
Right.
And that's one vision, of course. And it's that it may be a little bit more dangerous than what we thought. And this comes from detailed analysis of what was observed in Apollo 17 landing at Taurus Littoral landing site, the Taurus Littoral Valley on the moon. And you can see there's an image there on the far left. That's Jack Schmitt examining a boulder. So he was the only geologist that was launched to the moon during the Apollo project. And it happened at the very last flight, so December of 1972. Speculation, the original plan was to go to Apollo 18, 19, and 20. So we built 3 other Saturn V's that never got used for the Apollo mission. One was used to launch Skylab, and the other 2 ended up in museums on the Earth.
Right. Now, at this point, did they know they were the last Apollo mission?
Yes, definitely.
They did?
Yeah, they do at that. They knew at that point. So during Apollo 18, 19, and 20, I'm sure NASA would have sent up more geologists, more scientists to explore it. It just made sense. So, but anyways, Jack Schmitt has a distinction of being the only scientist, trained professional scientist, that had gone to the moon. Now, by examining the soil and the rocks that were brought back and the landscape, such as the large boulder that you see here, and also instrumentation like seismometers that were left on the moon, not just the Apollo 17 site, but at other sites as well. And a seismometer, you can see there's the one from Apollo 11 on the right-hand side, that image of one of them. What they discovered was they speculate that the boulder that Jack Schmitt is examining on the left then was actually dislodged, so it had moved from its initial location by a moonquake that occurred about 28.5 million years ago.
Okay.
And it turns out there are a lot more what they call these strong sort of surface moonquakes that occur.
Okay.
And so a paper was recently published that describes this in Science Advances. Paleoseismic activity in the moon's Taurus Littoral Valley inferred from boulder falls and landslides. And one of the conclusions, and you can see this written up in the abstract, is that shallow moonquakes from likely active faults may pose a potential hazard to long-term outposts on the moon himself.
I can see that.
So there can be an issue where moonquakes can actually cause, maybe some base that you constructed for some of that infrastructure to collapse in on itself.
Right.
So when we go back to the moon, we should keep this in mind. Build things so they can withstand moonquakes.
And when we know things collapse, because we've got openings down into lava tubes that have been photographed and imaged. So this is a concern. I hadn't thought about that myself, but
yeah, the other thing is we have a lot of these scarp features, which the abstract points out to. Right? There's one that's near the Apollo 17 site. In fact, if you go to YouTube, you can look at one of the video of the landing of the lunar module and the taking off. And in that, you can actually see some of these land features that we're talking about because you get this nice wide sort of field of view of what's in the vicinity, general vicinity. And you can see those sort of features. And in some of the other Apollo missions too, you can see that. So there are a lot of geological, quote unquote, hazards that we have to worry about, and also a lot of geological signs of activity on the surface of the moon. The moon's not a dead world in that sense.
Absolutely. Yeah. It's got stuff still happening on it. And we did have a question from another one from Extra Bulla.
Yep.
What about a space station around Mars instead of landing, since supplies regularly? Thoughts?
Yeah, that's part of the whole thing of the Artemis is going back to the moon, and this way it's the gateway.
Right.
That would be a station that's in orbit around the moon that would allow spacecraft to go from the Earth to the moon, hook up to the gateway, and then transition from the gateway on a lander down to the surface of the moon itself. And then beyond that is go to Mars and do a similar sort of thing.
Right.
So you would have a station in orbit around Mars that you could resupply stuff and just have vehicles specially designed to land on Mars that would transition down to the surface and then back up to the space station.
Right.
And then the main craft would be hooked up there, docked with it. Then it would transition from that space station in orbit around Mars, then back to the Earth.
Yeah. And Andy Weir got that idea, goes over that idea in his book, The Martian, or something very similar with the, I forget what the name of the Orion, I think is their mission, his mission, so-called mission ship. And so there was a big mission ship that carried you to Mars from Earth vicinity, dropped you picked you up, went back. And he got that idea because he was talking to NASA scientists and officials. You know, what would you do? What would this look like? How would you do this? And so I highly recommend the book. There's a lot that's still wrong with it, but the gentleman was talking to people who know. And so a lot of it is actual speculative. How would you work this mission?
But yeah, that's sort of a natural type of infrastructure that will be built in our solar system. And of course, if we don't do it as the United States, other countries will.
Right. And
that's the thing.
And to me, why aren't we talking? Why aren't we enhancing this collaboration we have with ESA and JSA, the Japanese and European space agencies? Why do we have to do it? Why can't we, as a more global entity, do it?
Well, that was the part of this whole business with the International Space Station, right? It was be a proving ground where we could get along with other countries in space, build things, share common resources.
Right.
You know, and then each of us pay our portion.
Pay our share. Yeah.
And then we could continue that to other things, like going to the moon or going on to Mars. Now, there is the Artemis Accords. There are many countries that have signed up for that, and that's the idea behind that. That's not just the United States. There are other countries involved that could hopefully share the financial burden with the U.S. as well, and the expertise that they may have that we lack a bit on, or resources and so on, that we all could share that. So it would be the Earth going back to the moon, the Earth going on to Mars, not just the United States.
You want to get politics out of science. That's one of the big ways. Get the politics out of science. Stop throttling scientists by saying, oh, wait, that's state secret. You know, get out of the way. Let us do our jobs. Just put it all in a big pool of resources and say, here, what do you need?
And then with all the stuff that goes on, you know, hacking and cybersecurity, a state secret, how long does it remain a secret?
Depends on which country, apparently, but that's another matter entirely, too.
So there's that. So that's going to be interesting to see how this plays out, given the budgets and what Congress eventually and the president decide at the end of it all. And we're still waiting to see how that all plays out.
There you go.
Okay.
So
the last sort of item I wanted to mention today is a new measurement that was done in the last few months of the lifetime of the neutron.
Okay.
So the neutron's lifetime has been on the order of about 15 minutes or so. And people sometimes are mystified by the fact that the neutron has a lifetime that's that short. Because if you look, for example, you look at common elements, let's say helium. That's the stuff you suck in from a balloon and then you talk funny for a few seconds. And you take helium, so what's it composed of? It's composed of 2 protons. That's what makes it an element, helium. If it had one, it would be hydrogen.
Right.
So we're taking helium. And in its most common form, helium not only has 2 protons in the nucleus of the atom, it has also 2 neutrons. Mm-hmm. And along with that, it needs to have 2 electrons that balance out the electric charge, unless somehow 1 or more electrons got removed or added to the helium atom.
Right.
But in its neutral form, its most common form, 2 protons, 2 neutrons in the center, 2 electrons on the outside of the nucleus of the atom itself to balance the charge. Now, if you take a helium atom like that, it is extremely stable. In fact, hydrogen and helium were formed in the very beginning of the universe, 13.8 billion, that's what it'd be, billion years ago.
Right.
And those helium atoms are still around today.
Unless they've been consumed in heavier mass stars.
But on average, those helium atoms are around today, right? There's a helium atom out there in space that was formed in the heat of the Big Bang.
First few milliseconds of the Big Bang. Yeah.
So that helium atom then is around today, so it's extremely stable. So what's this thing about this lifetime? And by the way, the lifetime, as I mentioned, has been measured now to be about 877.83 plus or minus 0.3 seconds. So look at the precision on that, Robert. 0.3 seconds. That's amazing when you think about it.
That's really timing it.
But so this is just under 15 minutes.
Okay.
So a neutron then decays. It is not stable.
It kicks out an electron and a proton. Correct?
Yes. So if you take, this is the way to think about it. Let's say you take a helium atom, you take special tweezers, and you pluck out a neutron from the center of the helium atom, and you just leave it somewhere by itself and don't interfere with it at all. Put it in an isolated container somehow, and just watch it. it'll decay in about 15 minutes, a little less than that, but about 15 minutes on average, into a proton, an electron, and a strange beast called anti-electron neutrino.
Okay.
Okay?
So not to be confused with the tau or
Right. So the proton is positively charged. The electron is negative charge. So those two charges cancel each other out. If you take a positive one and add a negative one, you get 0. And a neutron has no charge. That's where its name comes from. Neutron, neutral, in terms of the charge. And the anti-electron neutrino has no charge at all.
Okay.
Okay? So then if you add up the masses of those individual particles, the proton, the electron, and the neutrino, they are less than the neutron's mass, because some of the mass is converted to the energy, like the kinetic energy of the movement of the particles.
Yeah.
Okay? Now, you might ask, why then does an isolated so-called free neutron decay? Because if you take a proton and pluck it out of a helium atom and leave it by itself,
That's called a hydrogen atom, and
right?
who cares?
Well, no, if you take a single proton and leave it by itself, we tested this looking for proton decay because it's actually a prediction and one of the grand unified theories, which we can get into at another time.
Yes, is proton
And
decay.
they've estimated that the lifetime of a proton is like greater than 10 to like the 37 power in years, right? Like huge number, right? So
Yeah, I call that stable.
right. So the proton doesn't decay, but why does the neutron decay? Well, the neutron is a little bit more massive than the proton. And because the neutron is a little bit more massive than the proton, when the neutron decays, it goes into a lower energy state.
Oh, and that's what everything rolls downhill.
Yes, everything wants to get to the lowest energy state possible. So the proton can't get to a lower energy state. So
Okay.
it doesn't decay. But the neutron can get to a lower energy state by going through beta decay, as they call it, into a proton, electron, and a neutrino.
Okay.
And so energetically favorable for the neutron then to decay.
And that's why then when they're combined with a proton, they become stable, because each of those particles are actually exchanging a gluon
Right.
in the strong nuclear force.
Yes.
Which means they're actually oscillating which one's the proton.
Now, why it takes 877.83 seconds for a neutron decay, that's for a different podcast. And I don't think anybody really knows the answer to that.
No.
So that's something else.
But that's kind of cool. That's good stuff.
It's neat when you think about that.
Yep.
Okay, so I think that's the end of today. So
Okay.
if you're interested in this kind of stuff, like why does it take
877
seconds for a neutron decay? Why not a millisecond? Why not 10 years?
Right.
Those are some of the things you can work on. And to do that, of course, you need to go to higher education. And one of the places you can go for your higher education is the University of North Dakota.
We'd love to have you here, virtually or in person. Come join us, talk to us. You know, we're here. We love talking about this stuff, if you haven't guessed, after 3 years.
Lots of programs to choose from, and you don't have to just be in STEM. You can go into humanities, or you can go into anything else that you like to.
Right.
So come to the University of North Dakota.
Come join us.
At least check us out.
Absolutely.
Don't dismiss us. Just come here and see what we got to offer.
Yeah.
Now, our next podcast will be next Tuesday, August the 12th, at the same great time. Hopefully, we won't have any technical issues this time.
Lord.
I'm scared to have guests because we will run into a technical problem.
Almost every time lately. So.
We're going to try to get through a few of these podcasts first to make sure we don't have any issues, and then we'll start bringing guests on board. So
Excellent.
we'll try
because
that.
We don't want to do this. And by the way, thank you, Tanis, for listening from Nuremberg, Germany.
Yes, thank you very much. And the other thing is, we always leave you with a quote at the end of our podcast. So fittingly, the quote is from the commander of Apollo 17.
Nice.
So Eugene Cernan. Unfortunately, he passed away in 2017. And I noticed after the Apollo program, when he left NASA, he did a lot of work, like for news media. You see him a lot on TV channels like ABC, if I remember, and did a lot of sort of promotion of the space program, including during the shuttle program and so on.
Right.
And so the quote is actually the last words, at least till this point in time, that were ever spoken by anybody when they were leaving the surface of the moon.
Okay.
And this is December 1972. So this is what Eugene Cernan said. And as I take these last steps from the surface, back home for some time to come, but we believe not too long into the future, Unfortunately, it took a
Yeah.
long time. I believe history will record that America's challenge of today has forged man's destiny of tomorrow. And as we leave the moon at Taurus Littoral, we leave as we came, and God willing, as we shall return with peace and hope for all mankind. Godspeed the crew of Apollo 17.
Nice.
So if you like this podcast, please remember to give us a thumbs up.
Thumbs up.
Smash that thumbs up button.
And hit that like button, subscribe, all of that good
All
stuff.
those wonderful things, and we'll see you next time. Thank you very much.
All right. Have a good night, folks.